Right after Donut Lab announced its so-called solid-state battery technology capable of charging from 0 to 80% in just 4.6 minutes at 11C. It sounded like the breakthrough the industry had been waiting for. So, what exactly is inside Donut Lab's battery pack? Is it truly a solid-state battery or just a semi-solid one? Let's deep dive into this episode today and become our first subscribers for the channel. Thank you. Fellas, evidence circulating within technical communities suggests that the core component may actually be a semi-solid lithium NCM pouch cell supplied by Enbar in Shenzhen. A pouch cell architecture combined with lithium-nickel-cobalt-manganese chemistry is not revolutionary. It is a mature, well-understood lithium-ion system. Semi-solid batteries typically use a gel or hybrid electrolyte that reduces flammability compared to conventional liquid electrolytes, but they still rely on lithium-ion transport in a partially liquid medium. That is fundamentally different from an all-solid-state battery, where both electrolyte and separator are entirely solid, often ceramic or sulfide-based, eliminating liquid phases. Why does this distinction matter? Because the mechanical stability, dendrite resistance, and thermal tolerance of true solid-state systems arise precisely from the absence of liquid electrolyte. Calling a semi-solid lithium NCM pouch cell a solid-state battery blurs a very important engineering boundary. What does battery physics say about Donut Lab's battery? Looking at the voltage curve revealed in Donut Lab's introductory video, we look for traces of chemistry. The charge and discharge profiles shown bear a striking resemblance to typical NMC systems. The nominal steady-state voltage appears to be around 3.6 to 3.7 volts per cell, a classic hallmark of lithium NMC chemistry. Even some sodium-ion systems have distinct steady-state behavior, but the curves presented resemble known lithium-ion dynamics. So how can the company claim the battery is lithium-free if the electrochemical behavior reflects lithium intercalation almost perfectly? In battery science, voltage curves are like human DNA. They are difficult to fake because they reflect the thermodynamic properties of the materials involved. If it behaves like an NMC and charges like an NMC, then what else could it possibly be? The answer seems obvious to everyone at this point. Why Donut Lab batteries said to remain stable at high-intensity charging? Donut Lab claims their batteries are more stable at higher temperatures up to 90 degrees Celsius. Chemically, this raises many questions. Solid-state batteries can indeed exhibit better heat resistance because solid electrolytes are non-flammable and structurally stable. But if the system is semi-solid or liquid-based, then the enhanced stability at 90 degrees Celsius requires a more detailed explanation. The testing process only shows a final result, not specifying how many times the battery underwent heating. In high-energy lithium-ion systems, especially at 11C charging rates, internal resistance generates a significant amount of heat. At high temperatures, side reactions accelerate, the risk of electrolyte degradation increases, and the probability of overheating increases dramatically. Most commercial lithium-ion batteries are designed to operate safely below 60 degrees Celsius. Let's see the commercial feasibility. Why has cycle life data not been disclosed beyond a single demonstration? Major automakers such as Honda have repeatedly stated that cycle durability remains the primary barrier to solid-state commercialization. Even promising sulfide-based solid electrolytes struggle with interfacial degradation after hundreds of cycles. If Donut Lab can truly charge at 11C, reaching 80% in 4.6 minutes, accelerated testing becomes straightforward. Running 1,000 full cycles at that rate would take less than 1 week of continuous operation. In other words, within 7 days, a lab could generate long-term durability data. So why is there no publicly available 1,000 cycle graph at 11C? Why only one-cycle demonstrations? In battery engineering, longevity defines viability. A cell that survives one spectacular charge means nothing if capacity fades to 70% after 200 cycles. What about energy density? Marketing often emphasizes speed, but practical EV adoption depends on watt-hours per kilogram, based on the disclosed dimensions and capacity hints. The projected energy density does not appear dramatically higher than high-quality NMC pouch cells already on the market, which commonly achieve 250 to 300 watt-hours per kilogram at the cell level. If the Donut Lab cell operates within that same window, then its innovation lies primarily in charge rate rather than energy storage. And high charge rates come with trade-offs. Lithium plating risk. increased impedance growth, and structural stress. Without clear data demonstrating superior gravimetric or volumetric energy density, can we truly call it next generation? Another subtle yet revealing observation comes from visual inspection. In demonstration footage, the battery pack appears to exhibit slight swelling during operation. Pouch cell expansion is typical in liquid or semi-solid lithium-ion systems due to gas generation and mechanical stress during cycling. All solid-state batteries, by contrast, are generally more rigid because their solid electrolytes do not permit the same internal gas formation dynamics. If expansion is visible, does that not suggest the presence of a liquid or gel component? Even minor swelling is a physical clue pointing toward conventional electrochemistry rather than a fully solid architecture. So, is this technology a breakthrough or a branding exercise? The origin of the cells, potentially sourced from Enbar in Shenzhen, aligns with semi-solid lithium NCM technology. The voltage curves resemble lithium-ion behavior. The thermal claims exceed typical lithium-ion thresholds without detailed supporting chemistry. The absence of long-term cycle data contradicts what we know about durability challenges in solid-state research. The energy density does not clearly surpass established NMC cells, and the observed swelling hints at liquid components within the system. Does that mean the technology lacks value? Not necessarily. Semi-solid-state lithium batteries can indeed offer improvements in safety and faster charging advantages over conventional liquid systems. Gradual progress is crucial. But calling it a complete revolution in solid-state batteries requires extraordinary proof, not a marketing statement for investors. Ultimately, what will settle the debate? A publicly available 1,000 cycles performance graph at 11C, accompanied by independent verification and full material disclosure, would instantly change the discussion. Detailed electrochemical impedance spectroscopy data, overheat test results, and third-party certification would provide credibility. Until then, skepticism isn't pessimism. It's a standard engineering principle. So, is Donut Labs' solid-state battery truly a solid-state battery? Or are we witnessing a semi-solid lithium system marketed in bold terms? Leave a comment below if you already have the answer. Thank you, fellas.